Okay, we are taking a look at a new section. It starts with an idea called scatterplots, and we're looking at something called correlation. It doesn't fit beautifully with the story, the big overall story of getting to inferential stats. The best you can maybe say is that it's one last piece of descriptive statistics that we're going to hit. So let's dive in. The idea is this. We want to take a look at two variables, or two I don't knows, okay? So data came in, and we're taking a look in this instance at how people did on their third exam score and how they did on their final exam score, okay? We've got two pieces of data, and we just want to see them. What we're going to do here to see if there's some kind of association between these two things is we're going to make this a set of ordered pairs. Do you remember this? This is just the x and y. This is graphing. You know, we've made a coordinate plane here. Our x is going to stand for the third exam score, and our y is going to be the final exam score. So all I'm doing is mapping out everybody's third score, and then I go up to their final exam score. So this person got like a 64, got a 180, something like that. So we're going to put them all into a picture. And now we want to describe them. Before we do, though, we need to take a look at one clear idea. Is there, among these two variables, among these two pieces of data, does one of them explain the other? Now, it's not going to change what we do today, but what we do next time is a really big deal. So we first want to ask, does one of these explain the other? Here's the idea. It comes just from this. In high school math, if you had an equation like this is the equation for a line. And what this is, you drop something in for x, you crunch all the numbers on it, and you would get y out. Okay, think of it kind of like a machine. X goes into the machine, you crunch it, y comes out. Well, x here is called the independent variable. It's the one going in. Y is dependent upon what x you put in. The same idea is here. There's one of them that's explaining what's going on. You're going to put that in, and you're going to see what you get as a response, like independence and dependence, okay? Just like this. So in high school, when we said the independent one was the x, we're going to do the same thing. The independent one is the explanatory. So look here. Do you think there's a connection? Sometimes there is, and sometimes there isn't. But there's some natural way that you could think, did the third exam score explain how you did on the final? Now, this one's not perfect. They get better than this, but you can make that argument that how you're doing as you did the third test may play a role in how you did on the final exam. Other ones might be, does the height of a basketball player influence their free throw shooting percentage? Does the weight of a car explain its gas mileage? So look at that one. Clearly, you'd think that the weight is explaining how well a car does with its gas mileage. So if you've got an explainer, you're going to put it along the x-axis. And then you put your responder as the y. Now, you've created this thing called a scatterplot. And just like we did with histograms, the best we can do with this for now is we're going to start describing it. Well, as we describe it, there's three things about it which we would like to describe. They're the form, the direction, and the strength. So when we talk about form, what is it? Well, the form are only choices for this class. Or do the dots appear to be making a line? Is there something linear going on here? Or is there nothing at all? It's just a random pattern. For direction, we're going to be looking at, do the dots appear to be going in a positive direction or a negative direction? And then lastly, we're going to describe this by telling the strength. At first, we're just going to say weak, moderate, or strong, but we're going to make some math kind of back up our ideas with something called correlation. Okay, so let's look here. Here's my third exam score, final exam score. I got a bunch of dots. What about the form? Now, I know it isn't very good, But if there is anything even remotely appearing to be a line, we're going to call that linear for this class. So if you look at this, it's not very good, but there is something that vaguely resembles a line flowing right through there. So we're going to say that our form is linear. Now for direction, we've got these choices: positive, negative. Well, for 0, what you would expect is just a shotgun blast all over the place, no pattern whatsoever. But if we're like climbing the hill, this would be like a positive slope in algebra. As we were climbing up the hill, as we go left to right, that's a positive. If we have a negative slope, the dots appear to be heading downhill, where 0 is nothing at all, just all over the place. Okay, we've got one last part of this before we're going to get into correlation, and that's the strength. We're going to take a look at how good of a line do these make. So a moderate strength, there's a line there. It's not very tight, but there's definitely a line. Now, it gets strong when you start to really tighten up around a line. And then this would be perfect. The association between these things, it's on a perfect line, perfect correlation, perfect association. Now, these are the same ideas. This one's negative, so this would be moderate going downhill. This, like I said, this is no correlation. And then this nice smiley face is not really all that important, but this is not linear here. So this is completely irrelevant. It doesn't make a line, so we would just move on from that one. Okay, now this nasty thing here is the formula for the correlation. Now, what we're going to do, though, is we aren't going to do this by hand, but correlation is going to give us some real meat. It's going to give us some real numbers to talk about instead of just saying, well, you know, I kind of think that's a moderate correlation, or I kind of think it's strong. So what we're going to do, what you need to do is clear out your list 1 and your list 2 and your calculator. You're going to put these in list 1. You're going to put these in list 2. And then you're going to do something, ln reg a plus bx. Now we're going to talk about this in our entire next lecture, but it is under calc, I believe. So like you would do for one variable stats, you're going to go lower there. You're going to find ln reg a plus bx. Once you've got that, you're going to run it off list 1 and list 2. Now, what you get is going to include a lot of stuff, but you should get a value for r. Now, if you don't have that, if r did not appear on your list, what you need to do is go down all the way to you have a catalog of all the options on your test, on your calculator. It's above 0. You got to hit second to get there. Go to catalog. You're going to scroll through all the options until you find something that's called diagnostic on. Hit that once to bring it to the front screen. Hit it again to make it say done. And now run the ln reg again. You should have the r if you didn't have it before. Okay, so now we have a correlation, and this is a number that's going to tell us if there's a strong association. It's going to tell us more than just strength. It'll also tell us the direction, and I'll tell you all about that here. So here's what we get when we get a value for correlation. It's always going to be between -1 and 1. Every time. There's no other choices. -1 is a perfect line, so is 1. But the difference between them is the negatives tell me that the dots are going downhill. The 1 tells me that they're going uphill. 0 then is no correlation at all. It's that shatter blast all over the place, scattered all over the place. And then we have any variation between there. So -1 to 0, 0 to 1. Okay. Is there anything else here I want to say? Okay, I told you all those things. Now, it's a little subjective, and you would think that like 0.5 means that it must be a moderate line, but the truth is 0.5 is still not very good. So for my sake, I'm going to say 0.8. Some textbooks may say 0.7, but if you want to tell me that you've got moderate, I want to be about 0.8. And if you're saying strong, I definitely want to be above 0.9, probably even 0.95. but I'd be okay with 0.9. So again, there's some subjectivity to this, but moderate, you got to be around 0.8 or better. Strong, definitely over 0.9, maybe closer to 0.95. Now, this is another mathematical version of this equation. It's completely equivalent to the other one, exactly the same. But the reason I'm showing you this is because it teaches some important lessons about correlation. You're not going to have to do this by hand, but does this look familiar to you? Look what this is. This is x minus a mean over a standard deviation. Now, it does this. That is our z-score formula. X minus mu over sigma, same thing. And what this formula did was it standardized our data. But in essence, what it does, it takes units away. It makes units irrelevant. And it does the same in the y. So when we deal with correlation, correlation does not have a unit because everything involved has been standardized. It's had the z-scores run on it. And it's finding an average distance away in each of the directions. But the point is that when there are no units, it doesn't matter if we change the units. Let me give you an illustration. If I wanted to see if there was an association, a correlation between the number of pages in a book and the price at which it sells, wouldn't you say that that's probably the case? Doesn't the number of pages probably explain the cost that the book is going to have? You would think so. Well, what if we did that, we examined that in the United States, where we're using the standard system, and the cost would be in dollars? Well, what if I jump on Amazon and I look at all of the very same books, but now their cost is in pounds? Well, so would this change anything? So in the United States or in Britain, is there somehow a difference in the association between the dots, between the pages and the selling prices? There shouldn't be, and there isn't. So changing the units does not affect the correlation. Now there's one variation of this that you're going to see in our activity. I'm going to let you kind of think through that in just a minute. What else do I got for you? 2 last slides. This is not going to be a focus for me. If we were in a higher course, I might hit on this a little more, but it's called the coefficient of determination. If you see this in the textbook, it's basically the idea that about how good of a job is what we have doing of explaining this relationship. It's very similar to correlation, but it's a slightly different way of attacking it. Mathematically, though, all it means is it's r squared. That's it. So if you see the coefficient of determination or something says, hey, the percentage of variation in y that's explained by x, as confusing as that is, they're just asking for the coefficient of determination, r squared. So take r, square it. Okay, last slide. Correlation does not mean that, so we think there's a strong correlation between two things. That does not mean we've established a cause and effect relationship. That doesn't mean the height explains the basketball player. That doesn't mean it doesn't prove it. I forgot my earlier illustration. It doesn't mean the third exam score causes your final exam score. None of that. Here's the illustration that's used most often. If I were to plot a scatter plot with trying to find the correlation between ice cream sales and shark attacks, what I would find is that the correlation is very strong. So ice cream sales and shark attacks. Does that mean that ice cream sales is causing sharks to attack people on the beach? It doesn't. There's something else going on there called a lurking variable that's hiding beneath the surface, and that's the weather. So just because you establish a strong correlation, you need to run some experiments if you want to try to establish causation. Okay, that should get you started.